Okay. Hey guys, we're now going to do calculus on power series. Essentially, we're going to take what we've learned about power series, and one of the things we learned was getting interval of convergence, and now we're going to do calculus on them. We're going to do derivatives and integrals, and you're going to find it's really, really easy because there's two ways to do it. You can either do your calculus on the general term, take the derivative or antiderivative of the general term, or you can do your calculus on the actual individual terms, and it'll work out either way. Okay, let's go for it. Calculus on power series. Alrighty. Here's the first example. Here's my power series. I've got some function f of x, and I'm going to express it as a power series. The sum is n goes from 1 to infinity of x to the n over n. That's your classic power series. Okay. And just so you know, this ends up being x plus x squared over 2 plus x to the third over 3 plus dot, dot, dot. Someone tell me, what's an expression for f prime of x?
X to the n minus 1.
Okay, Andrew says x to the n minus 1. Andrew, how did you get that?
Because if you take the derivative with respect to x, you pull the exponent down in front and then decrease it by 1, and then the ends cancel out.
Yeah, you guys okay with that? I mean, the n is just a constant, so if you take the derivative, you're not going to be dealing with a constant. You're not going to do some weird quotient rule thing. The only thing you're taking the derivative with respect to is x. And the derivative of x to any power is that power times x to the one less than that power. You see? So yeah, the derivative is going to be this, x to the n minus 1. Alrighty? Now, let's say you're not like Andrew. Let's say you don't feel like taking the derivative of the general term. Could you take the derivative of the individual terms? Yeah, sure. Right? The derivative of x is 1. The derivative of x squared over 2 is x. The derivative of x to the third over 3 is x squared plus dot, dot, dot. If I go term by term, do I get the same answer as I get here? Yeah, it's the same answer. So you've got your choice. You can either do it to the general term or you can do it to the individual terms. Now, one thing though is usually the AP exam will require you to find an expression for the general term. So even if you don't take the derivative of the general term, you'll end up having to use your cleverness to find that general term anyway. So you might as well just take the derivative of the general term. But I just want to say again, you can always check your answer. Once you take the derivative of the general term, go ahead and get the derivative of the individual terms and make sure it's the same darn thing. So there's a lot of ways that you can ensure that you don't get wrong answers here. Okay, hey, that's the derivative. Now, here's another question. The interval of convergence. I want to get the interval of convergence of this guy. Does anyone have a guess? What do you suppose the interval of convergence is? From where to where?
1 to negative 1.
Okay. Andrew says from 1 to negative 1. Someone besides Andrew who's answering every question. Why is from 1 to negative 1 a reasonable guess? For your values of x? What happens if you plug in 1? What happens if you plug in negative 1? What special type of series do I get if I plug in a 1 for x? Yeah, what's that? Convergent. No, not convergent. Divergent. And what do we call that divergent series? Yeah, it's the harmonic series. So in the harmonic series always ends up being like a borderline series. Okay, so yeah, I'm thinking 1 is a good guess, and certainly if I plug in, since 1 over n diverges, certainly anything bigger than 1 over n is going to diverge. So I'm thinking, okay, 1, but anything less than 1 probably is going to converge. You see, so you can always guess, but if you don't feel like guessing, what's the definitive way for me to find the interval of convergence here?
Ratio test.
What's that?
Ratio test.
Yeah, ratio test. So let's go ahead and do the ratio test, okay? You know what? I mean, shoot, let's not use our cleverness. Let's just do the ratio test on that guy. The limit as n approaches infinity of the n plus 1th term, x to the n plus 1 over n plus 1 over x to the n over n. And we're going to set that less than 1. And this, you know, Lauren, one of the reasons I didn't go over that quiz problem with you is I knew we'd be doing ratio test in the course of this lesson. So there we go. And then I'm rewrite this. Instead of dividing by this fraction, I'm going to multiply by its reciprocal. So I've got the limit as n approaches infinity of x to the n plus 1 over x to the n times n over n plus 1. And I'm going to set that less than 1. As n goes to infinity, this guy goes to 1. And x to the n plus 1 over x to the n is just x. And so I get negative 1 less than x less than 1. Yay. What's the radius of convergence?
1.
Yeah, 1. Half the diameter of convergence, the radius of convergence. Okay, now what do I have to do?
Check in.
Yeah, check the endpoints. Let's check the endpoints. Let's plug in 1 and let's plug in negative 1. And that's literally how, you know, quotidian, how prosaic checking the endpoints is. You just literally plug the endpoint in, you know? So when you plug in 1, I end up with the sum is 1 to infinity of 1 over n. Okay, tell me, does that series converge or diverge? Sure, it diverges. It's the divergent harmonic series. Okay? Or I can plug in negative 1 to the n over n. Does that guy converge or diverge? Why do you say it converges? Thank you, because it's an alternating series. And now, all I have to do is look at its positive cousin and ask myself, do the terms get smaller and smaller, and is the infinitieth term 0? And if both are true, this guy's going to converge, because alternating series converge more easily than non-alternating series. So this guy converges, okay? And so now, I've got my interval of convergence. Yay. And don't forget that guy right there, or you don't get full credit on your next exam. Well, here's the last thing I need to tell you about calculus on power series. Guess what? I do not have to do ratio test on the derivative. You know what the interval of convergence of the derivative is going to be?
Negative 1.
Yeah, the same darn thing, except the endpoints may be different. And so that's the last and new thing I'm teaching you today, and that is interval of convergence on any derivative or integral of a function will be the same, except you have to recheck the endpoints. And so that's it. Let me write that down. Interval of convergence of f prime of x, f double prime of x, f triple prime of x, or integral of f of x, or any higher antiderivatives is same as f of x. So I don't want to see you doing 2 or 3 different ratio tests. Once you do the ratio test for f of x, you're done doing ratio tests. But now, of course, you have to recheck the endpoints. Oops, I forgot to spell that word completely.
Mr. Shane,
Yes.
on our test, if we write IOCR for the interval of convergence to the radius,
Sure.
can we just write that?
Yeah, whatever you want to do.
Okay.
I'm sure I'll understand it. Okay, so look at this f of f prime of x, okay? First of all, what's the interval of convergence going to be? From where to where?
-1.
Yeah, -1 to 1. Same as what we got there. The only difference is I'm going to have to check the endpoints. Well, I'll bet many of you could do it in your head. Tell me, does 1 work? No way. You plug in a 1, you got 1 plus 1 plus 1 plus 1 plus 1, and that diverges. Does -1 work? No way. You plug in -1, you get 1 minus 1 plus 1 minus 1 plus 1 minus 1, and that doesn't converge either. So that's it. That's your interval of convergence. So hey, here's an example I'd like you to do. And then I'm going to show you a couple of problems from tonight's homework, and then maybe we can go over assignments 22 and 23. Here, example number 2. Get the antiderivative of f of x dx. Please do that now. You've got an expression for f of x. Please get me the antiderivative. And then find the interval of convergence. Let me see if you guys can pull this off. And I'll help you. Or I'll show you. By the way, you should be getting a constant of integration, and that's okay, just call it C. Because you can't get what it is unless I tell you more information. Alrighty, well hey, I'm hoping most of you can get the antiderivative of x to the n over n. What's the antiderivative? Someone besides Andrew, if you don't mind. So x to the n over n, what's the antiderivative? Is that?
X to the n plus 1 power over n times n plus 1.
Yeah, beautiful. That's all you do. Increase the exponent by 1 and divide by the new exponent. So you've got x to the n plus 1 over n times n plus 1. That's it. That's all there is to it. If you wanted to write out the terms, you know, you could get the antiderivative of each of those individual terms. So you'd have 1/2 x squared plus 1/6 x to the third plus, what is that, 1/12 x to the fourth? Did I do that right? Wait, antiderivative fourth, yeah, 1/12, 1/6, 1/12, etc. You know? Except for one thing, what did I forget here?
C.
Yeah, don't forget that constant of integration. And you can't know what that constant is unless someone tells you more information. Like if they tell you, you know, the antiderivative of f of x evaluated at 0 is equal to 12 or something, then you can get what that C is. Okay, and now here comes the next part, interval of convergence. Okay? Well, first of all, before I do anything else, what's the interval of convergence going to be from where to where?
-1 to 1.
Yeah, if you're thinking -1 to 1, you win. That's it. But now the issue is the endpoints. If I plug in a +1, if I get integral of f of x evaluated at x = 1, that is, I'm going to stick a 1 in here. Tell me, does it converge or diverge? What kind of series is this looking like? What kind of series is this going to be similar to, Daniel? Oh, I'm sorry. I thought you had to. What is it? Is this going to converge or diverge? Yeah, converge. And why? Why does it
It's a
converge?
telescoping series.
True. Who said that? Telescoping series. Yeah, good for you. Yeah, it's a telescoping series. Anyone thinking, what kind of series? Like if you're going to do limit comparison or direct comparison, what are you going to compare this guy to?
And 1 over
Yeah,
n squared.
1 over n squared. And 1 over n squared converges, right? So you see, whether you think of it as telescoping or it's like 1 over n squared, it's in the 1 over n squared family, this guy's going to converge, okay? So I get to have the equal sign there. Tell me, how about evaluated at -1? Is that going to converge or diverge? If I stick a -1 for x, does that converge or diverge? Well, hey, and there's a very good reason why it's going to converge. I don't even have to do the 2 criteria. How do I know for sure that the alternating series is going to converge?
Because the positive cousin converges.
Yeah, thank you very much, Fatima. Because its positive cousin converges. If the positive cousin converges, then guaranteed the alternating series converges, because alternating series converge more easily than their positive cousin. You know what I mean? So yeah, so for sure that's going to work. Alrighty. So yeah, so I just want you to see when I did calculus on this series, I took the derivative, same interval of convergence, but neither endpoint worked. Antiderivative, same interval of convergence, but now both endpoints work. You see? So that's what you're going to have to do. And that's it for calculus on power series, except I need to show you a couple of problems now. But any questions or issues on what I did? Okay, then, tonight's homework, do you remember this little packet that I gave you that we were using day after day after day?
Yeah.
There is one aside that you didn't use, and that was the second side of the packet that says Larson, page 604. This is now the time that you get to use it. You're going to do 4 of these problems for homework tonight. And in order to prepare you to do those 4 problems, I'm going to do problem number 28. I'm going to do one of those problems now. And then I'm going to give you a heads up on a couple of other problems, and then we'll be done. Then maybe we can go over homework. Maybe not. Alrighty. Okay, here. I'm looking at the page 604 sheet. Okay. They want me to approximate this to within 1/10,000th of the, that's a good way to deal with the donuts. Just eat them all. I agree. They want me to get the correct answer within 1/10,000th of the true answer. Now here's one problem. I cannot take the antiderivative of this. The cosine of x squared has no antiderivative. There's no function in the universe such that when I take the derivative of it, I get cosine x squared. So the only way to do this problem is numerically. Okay? When you do a problem like this on your calculator, what the calculator is doing is actually what I'm about to do. The calculator just numerically gets that integral in a very similar way to what we're doing, and it's just a calculator that does it really fast. Okay, so I need to express this as a power series. So what would you recommend I do? That is, I'm getting the integral from 0 to 1 of some function, but I need to express that function as a power series. Well, hey, I'll tell you, one way to do it would be to say, okay, I'm gonna get the Taylor expansion for this, or the Maclaurin expansion, because I'm gonna have it centered at 0. So I'm actually gonna do this. I'll do f of x equals cosine x squared, f prime of x equals the derivative of that, f double prime of x equals the derivative of that, f triple prime of x equals the derivative of that, and then I'll just construct my Maclaurin polynomial. Except, here's the problem. If I use cosine x squared, then the derivative of cosine x squared is negative sine x squared times 2x. And now the derivative of this, I'm gonna have to do product rule. So I'm gonna end up with negative cosine x squared times 2x times 2x plus negative sine x squared times 2. And then it just gets worse and worse and worse, you see? So I really don't wanna be dealing with cosine x squared. There's a technique I showed you a week ago where you can get the Taylor or the Maclaurin, thank you, you can get the Maclaurin expansion for cosine x squared without having to do product rule over and over again. What would you recommend I do?
Cosine x.
Who said that? Yeah, Fatima says cosine x. Just get cosine x. And once I write down cosine x, what am I going to do?
Square
Put all the.
Well,
x
don't
squared.
square all the x's, but
Plug in x squared.
yes, substitute x squared for every x. Absolutely. So that's what I'm going to do. I'm not going to do this crazy stuff. Okay? Now, by now, I'm not going to show you cosine x how I got it, because we've done it so often that you should be experts at it. Cosine x. Cosine x is an even function, so I know it's going to be this guy, because I know all of my f of c, f prime of c, f double prime of c's, they're either positive 1, negative 1, or 0. And so I end up with every other guy being positive 1, every other guy being negative 1. Are you guys okay with that? That's my expression for cosine x.
Yeah.
So now I'm going to just substitute x squared in for every one of these x's. So I get x1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial. Are you guys okay with that? I'm going to do that. Let me wait till you write that down, because this is how you're going to do 27, 29, 33, and 35. Just this way. You're going to substitute the Maclaurin expansion for that guy, and then you're just going to do your integral just like normal. Any question or problem on what I've done thus far? Because this is it. This is the heart and soul of the problem. Okay, then let's go ahead and take the antiderivative. Antiderivative of 1 is x. Antiderivative of this guy is x to the 5th over 5 times 2 factorial. Antiderivative of that guy is x to the 9th over 9 times 4 factorial. X to the 13th over, what is that, 13 times 6 factorial. And this thing is going to be evaluated from 0 to 1. Okay. Let's go for it. By the way, when I plug in a 0, what am I going to get? 0. So that's why doing the Maclaurin is so convenient. The lower bound is 0, we do Maclaurin, and then we plug in a 0, I get 0. So all I got to do is plug in 1. So I got 1 minus 1 over 10 plus 1 over, let me see, 4 times 3 times 2. That's 12, right? 4 times 3 times 2 is 24. So I got 9 times 24, which is 216, minus 1 over 13 times 6. I wish it was easier to do factorials on this stupid calculator. So I get 9360 plus 1 over 17 times 8 factorial, which is 685,440 minus, okay? They want my error to be within 1/10,000. So which is my first neglected term?
last one.
Yeah, this guy. I can't neglect this guy because this would get me a maximum possible error that's more than 1/10,000. So I can't neglect this guy. I'm gonna neglect this guy. And the reason I'm gonna neglect this guy is because it is the first term less than what the maximum possible error I'm supposed to have is, which is 1/10,000. So I'm gonna add these four guys up and get my answer. So that's how you're gonna do those four problems. You're gonna have to figure out what this guy is, antiderivate every term, and then stick in your bounds and write out terms until you get a term that you can neglect. Any question or problem on that? Okay, then I need to give you a heads up on 2 more problems, and then we'll be done. And tomorrow we'll go over all of our homework assignments, or Tuesday, because you know we're done with chapter 9 now. This is it. We're done with chapter 9. So we're ready for the test, which I think will be Thursday, unless Mr. Morrison prefers it on the following Tuesday. Okay?
I think we should make it Tuesday for the Morrison kids.
Really? Because they're dying?
Yeah.
Poor little Morrison kids. I feel so bad for them too. Okay, so number 29. Wait, no, it's 27. Do you notice number 27 has sine x over x? I hope everyone knows that constructing it, you're going to get sine of x, and then once you get that, you're going to divide each and every term by x. Does that make sense?
Yeah.
You'll get your expression for sine of x and divide each and every term by x. Number 33 is a little less obvious. 33, what you're going to, you have integral of 1 over x to the third. What you're going to have to do is get 1 plus x to the 1/2 power the hard way. That is, you're going to have to do f of x, f double prime of x, f double prime of x. And once you do that, then you're going to substitute x to the third for every x, for each x. So you're going to have to do that the hard way, and then substitute x to the third for each x. And that's how you get square root of 1 plus x to the third. All right, good luck, you guys. Are we done? Bye-bye.